So let's discuss another question from theory of machine. We have this is again a question on finding natural time period of oscillations. So a block is given and we need to find out what is once you displace a block as from the given position. If you leave it, it oscillates back and forth. Now why it will oscillate? Now at this position, if you leave it, it will come to a bottommost position where it will have some velocity, even though from the potential energy point of view the bottommost position will be stable, but uh, because of its kinetic energy it moves upward, and then when its speed decreases, because the speed will decrease at the expense of increase in potential energy, so it stops somewhere else. But at this point, when it stops, let's say here, at this point it will not be in equilibrium. There will be a mg gravitational force that will again try to bring it back to original bottommost position. So like this, it will just keep on oscillating if there is no friction. So from kinetic to potential, potential to kinetic, it will just go on oscillating if there is no friction. Okay, which is not a real. So this is not a real life scenario. But in real life, after one or two oscillations, it will stop because of the friction between the surface and the block. So but this problem we have to imagine that there is no friction and then we have to do it. So what we do with in these kind of problems, uh, we actually from the equilibrium position we assume that it's we take a distance x from equilibrium position or from a reference position, and we try to draw the free body diagram. So this is the normal force acting. Remember, it's normal to the surface, normal force acting from the surface, and mg is vertically downwards. And remember, this normal forces will be meeting at the center because it's a, so this is theta. Let's say this is theta. Okay, now what will I do is, along this direction I will apply the force, because along this direction only it will be exhibiting a tangential motion and it will have some acceleration. Okay, it experiences circular motion, so it will have both tangential and normal acceleration, but I am interested in the tangential because normal, the oscillation is along the tangential, right? So along this direction, taking the positive force upward, so mg, this is theta, so this will be theta, and the mg force will be mg sine theta acting in the reverse direction. I assume that this direction is positive. Okay, so minus the component here, mg cos theta is along the normal, mg sine theta is along the tangential, but in the reverse direction. So minus mg sine theta, and the normal force will not apply in this direction, in the tangential direction, because it's normal, and mat. So remember that for smaller oscillations, now sine theta, when theta is small, sine theta is theta, right? And also theta can be written as, well, in a circular motion for small theta you can write x is equal to r theta, right? So theta is x by r. So sine theta for smaller oscillations can be replaced by x by r. So this is x and this is r, and which is mat. So m gets cancelled, basically you get minus gx by r. Now remember that this is at, and at can be written as x double dot because it's acceleration in this tangential direction. So minus g by r. So this is, in order to bring this in standard form, x double dot is minus omega n whole square into x, because when you bring in this direction it is plus square x. Okay, and the acceleration is proportional to your displacement, and that constant is basically omega n whole square, right? So but the negative sign, because the acceleration is in the reverse direction of x. So this is our standard way when we compare any simple harmonic equation. So this is in the format of simple harmonic equation, whereas omega n square, from this comparison we get omega n square as g by r. Once we get omega n square, you can get time. So let's find out omega n. Omega n, g is 10, r is 10, so omega n square is 1, so omega n is basically 1 radian per second. Okay, and the time which it takes, so how do I get the time from omega n? It is 2 pi by omega n. So the time from this will be 2 pi by omega n, because this is a circular thing, so you have to convert in seconds. So 2 pi by omega n, which is 1, so this is 2 into 3.14158, so 6.28 seconds. So for one oscillation it takes 6.28 seconds. So this is a standard way of doing any problem of simple harmonic motion. You just from the reference position, you just displace it when you because in this position, if you have in this is why I am calling this as the equilibrium position. At the bottommost is the equilibrium position, because at that position, if you don't do anything, the body will stay there. So what you do is you displace it by amount x, and then at that point you study the free body diagram and see what is the unbalanced force. And because that unbalanced force here is from gravity, and that is towards, it will be a restoring force, because it's always acting in such a way that it tries to bring back to its equilibrium position. Now here also you can see this mg sine theta will be acting towards equilibrium position, right, because the directions is like this, mg sine theta. So that is the restoring force that will try to bring back to its equilibrium position. In fact, the presence of this restoring force is what brings the vibration in a system. So this is how you have to do force balance. Find out, bring it in the standard form. Acceleration is equal to minus omega n whole square into displacement. So once you get your equation to standard form, you get omega n, and from there on anything you can get, time period or natural frequency in hertz. Okay, so the answer is 6.28 seconds. Thank you.